Hi, this is Stats 1. This is Bill Foote. This is also Lecture 10, and I think we're actually up to Part 3. Part 1 was an introduction, give you the lay of the land of a model that we're building. Part 2 added some interesting features to that model, not the least of which is to make it a little bit easier for human decision makers to interact with it. Part 3 is almost all of the easy pieces. Now, that's all part of infer. The counting has already been done. We did that with Monte Carlo. We did the simulations. We did samplings of 12 vendors 10,000 times. Then we counted them up. We had formed some interesting hypotheses about means, standard deviations, and also correlation. That's a Greek rove, by the way. And going all the way back, we posed a couple of questions, but they're all around prices. What is not just the best price? As a matter of fact, I think our the Office of Corporate Counsel might say there is no such thing as a best price. There is a price, and you agree to it or you don't agree to it. What is the range of prices? If prices are too high, we'd be thinking of price gouging. If prices are too low, we would be thinking of perhaps low quality, in this case, coconut fiber, also known as coir. That's COIR. We got some initial data. This is a very preliminary proof of concept prototype type of situation. And we want to know what a high price and a low price is. But ultimately, we also want to have a good idea of the range of plausibility of prices for the purposes of writing a procurement contract with one or more of these vendors that we would call up on the phone or quoting 10,000 times each. Okay. Yeah, right. 10,000 times each. Never happened. That's why we burn transistors with George Gilder and waste simulations with Mike Draghi until bell rings and we have to get to work. Okay, so where is this model? Okay, let's bring it back up here. Lecture 10, Tale of Coir. And the results look like this, a little bit of writing behind it. Here was the modification where we can now ask what is the average FOB price in Indonesia. And we know that the average and the median, the arithmetic mean, and the median are the same. We also had a short discussion on the standard deviation of the sampled means. These are all sampled means. These are all sampled means with probabilities. And the sampled means, whatever distribution they might come from, for example, this odd-looking distribution, and that's just a sample of 12, okay? Not too much going on here. Very uniform, but it's odd looking at least. Okay, I hope everybody thinks it's odd looking. I think it's very odd looking. But even so, every time you take a sample, you find its mean and standard deviation, correlation with other samples, and you do that enough times, what happens is exactly what happens in our original work is the more data you add, the more that blue curve pinches in, squeezes out some of the information from the tails, concentrates it in the middle. Okay. And this standard deviation of 1357 is a fraction of the standard deviation of the Indonesian price mean. Mean standard deviation, the mean of it is the same as 320, but the standard deviation is 46, 47. And if you take that 4647 and divide it by the square root of the number of vendors we're calling, all right, in our simulation, in our minds here, you get this 13. So this is what we call the standard deviation of the sampled means, where the number of in the sample is just 12. Even though we ran this thing 10,000 times, that's just running something 10,000 times, but every time was a sample of 12. That's the key thing to remember. Okay, what are we going to add here? Well, let's see, what else can we add? Let me just move this over. That was interesting to do. There we go. We might even go up home here, by the way, just a quick. Yeah, but let's bold it. There we go. And there we go. That's a little bit easier to read. And we can modify this as we go along. But always check it with your client. The client is a person or committee or wherever that's going to look at this and say it's useful or it isn't useful. So far, we're going to make the assumption that we have had a chat with them. They now say it, oh, this is more useful than we thought it was. And, you know, you over deliver and under promise, right? Because you just don't know. It's a bit of a hedge on what you're doing because you don't know whether things will indeed work out. They've worked out fairly well here. So what we're going to do next is we're going to put in here, we have count, but we have sample, and that'll be the sample size. Okay, that's something we're going to want there. We're also going to want a lower and an upper limit. Okay, those are the other things that we're going to need to take. Well, not just sample and sample size, and I'm just thinking out loud here with my Excel spreadsheet, tolerance. Okay. So remember what we're actually trying to do here. Once again, let me bring this up. Let me put this in the simulation one. Sample size is 12. What we're actually attempting to do is, there we go. Can't lose that. Here's our distribution. Here's the plausibility index for a range of potential prices. And these are potential typical prices. Lots of news. Okay, the idea behind this kind of analysis, as it has always been since the beginning of time, of this sequence of lectures, is that our hypotheses are random variables. We would specify them and then figure out what a probability of the occurrence of that specification is. Okay, so we think mu's here, here we are, and then there's a mean of the means, okay, and a standard deviation of the means going out this way and out this way. So tolerance now is something. We might have a 5% tolerance, which means 95% of the time we want to see what prices will occur 95% of the time, centered, and this is critical, centered at the most plausible. So whatever this most plausible number is, you're going to go up, in this case, 95 divided by 2, or 47.5, or down. Symmetrically, it's also going to be 47.5. Well, okay, that's 95. Symmetrically, you have two tails. So 1 minus 0.95 equals 0.05. Call that our tolerance, but we then need to divide that by 2 to get 0.025. So we will have 2.5% here in this tail, go all the way up to, that'll be 95 right there, and 2.5 in this tail. And those will, from our, I guess, our corporate policy, somebody has to decide that is too high or too low for a price, an average price. Okay, that's where we're going with it. First step in going there, let's go to setups. This is already almost done for us, is to set up a set of tolerances. So I have one here, the 5% tolerance. So the client wants to say, well, what if the tolerance changes? Okay, so we'll let the tolerance change. Okay, we will let that change. So let's start out with a 1% tolerance. Let's go to a 5% tolerance. And let's do a 10% tolerance. I'm gonna offer one more, and that is a 20%. Let's do 25 because a lot of insurance companies have been known to price their deductibles on a 75th percentile, leaving 25% tolerance. Okay, so I'm going to leave that there in case somebody wants to think about the insurance aspects of this, which would be a really interesting thing to do. A few weeks of playing around with that. We don't want any borders there. Let's put a border around this. And let's also call this tolerance. Formulas, create from selection. Yes, let's use the top. And apparently I had it in there already, but let's change it. Okay, now we have a new definition. Let's format this as well. Again, for human beings. Okay, human beings typically would rather like to see this maybe in percentages. A little bit easier. Okay, we want to remember human decision makers is going to have a conversation about this. I'm not going to start 0.05. No, we're not going to do that. Okay, we're not going to play with decimal points and so on. Yeah, it's 1%. And actually, you can put a description here. Tolerance description of saying, remember we said at some point somewhere that 5% is the same as saying 1 in 20. Okay, 10% is what? 1 in 10. Anything to frame it to help decision makers come to a better idea. 1 in 4. Sounds almost like odds. 20 to 1, 10 to 1, 4 to 1. Yeah, very, very similar way to talk about it. And this is 1 in 100. So we could, I guess, use that, right? Yep, and use our index match to come up with the actual numerical duplicate of that and use that in a computation. Okay. So the upper and the lower is going to be half of this tolerance. The upper and the lower is going to be half of this tolerance, or this tolerance and this tolerance. Okay. So, okay, we have that. Now let's go to the EDA sheet. And let's put in some new labels, which we will then transfer over to the results sheet. Remember, nobody's looking at this stuff, just the analysts, people who need to see this stuff, all right? We said we're going to have a tolerance here. We should be able to spell it a little bit better, okay? And why don't we again use our pull down menu capabilities. And use the list. And I think we call it tolerance. And if we looked at that, oh, there it is. Oh, okay, good. Now we're eventually going to transfer that whole list over to the sheet. Now, why don't we do that now? Take this out of here. Put it over here immediately as is. There we go. So we're already beginning to think like a real user. Now, there's another thing we can use here in terms of this, and that's a text, but we're just going to leave it at 0.05. And this tolerance is actually going to come over from the EDA sheet too. Might as well put that in there. We'll do some formatting later. Okay, that's the tolerance. Sample size. Let's put that in here now. Sample size. And that's going to come directly from, let's bring it from the simulation sheet. Not the run, but this number right here. Okay, this way, again, we're using referential data properly. Okay, this number now is going to come from the user back over here. Whatever is in there. You see it's 0.05. Okay, all is good so far. All is good so far. Now, let's do a lower bound. And just like we said, lower 95 is what this will be called, which means 2.5%, lower 95 versus an upper 95. So let's make a bit of text here. Lower. Let's do a dash. And strap that together with an ampersand. And so we will take the chosen tolerance, which will be this number, and put it here. Okay, now let's do that properly here. Let's call this the formulas define name. Call this choice. Let's just do this tolerance underscore choice. Okay, I think we have that. There we go. A little bit hard to see. Okay, it doesn't like that. That does like that. Okay, good. This is called tolerance choice. Okay, so let's do it again. Lower, dash, ampersand, tolerance, choice. Okay, now actually we want the tolerance choice, yeah, 5%. We actually want 1 minus this number. Put that in parentheses. Let's see what happens. 95, lower 95. That's exactly what we want to have. Okay, and here we will have, might as well just copy this down. And instead of lower, we can put upper. Not upperer. There we go, upper 95. Okay. So we have the lower 95 and the upper 95 as labels. And the thing that we want to find out is the percentile. Oh, wait a second. This is exactly what we want to do here. So why not do this? Take this indirect. It's in this case of the mean indo. And let's use this to our advantage. Okay, it's value because it doesn't understand what the C20 is. So it should be 1 should be the tolerance choice divided by 2. Now that'll be the 2.5 percentile. There, 293 is the answer there. 293. Now the upper, and this won't be so hard to do. The upper will be very similar to this. Bring it up there. There we go. Let's see how we do that one. You know it's going to be much bigger than this. So instead of it divided by 2, we can take advantage of the fact that it's 95 plus this, or 97.5. Alternatively, we can just do 1 minus 2.5%. Get the same thing, right? 97 is 97.5. Okay. So this one 1 minus. There we go. 346. So we have way number 2 out of 5. Number 1 was Tukey, 25th percent fence, 75th percentile fence. Okay, look at how different they are. This one is definitely tighter than this one. Okay, definitely tighter. Let's get some wickets around this. There we go. Bring them all over there. And we are almost ready to go with our second method. Now we got a bit of a mess here. Let's get rid of this. Okay, because we're going to need some real estate. But we just take this and make this and copy it over. We bring all of that together, center it. Matter of fact, let's center it. There we go. And we might even use a little bit of, there we go, to indicate that there's a choice being made. Okay. Let's make sure we're using all numbers here. Beautiful. And for this one, let's just make it a percentage. There we go. We don't need any decimals there. And like we did with everything else, we made that. And now we're also going to do this. And there we go. Now the decision maker has that. But it's interesting, but we would probably also want to put it onto the graph. Okay, that's not a bad idea to do here. So let's do that. Let's make vertical lines. Okay, and it's going to be a little bit hard to see because it's all scrunched up here. because we are starting at 0 because it's on a reset. Now, before we do that, get rid of the mug here. Let's just look at this and see that it works. Yep, it works. See, those numbers look quite reasonable. And I say they're reasonable because they're similar to the 25 and the 75 fence. Again, look, it's a bit tighter. And if we change this to 1%, we see it's a little bit closer to the Tukey, which tells us something. The Tukey fence business here, it's a little LLC out there, John Tukey, is about the same as saying a 1% tolerance. About, okay, that's fairly typical. But let's see if it is indeed typical. Let's go back to the average. 285. Yeah, it's close. Matter of fact, it's a little bit more rigid. See, it's different. Yeah, but it's in the same ballpark as the Tukey, the 1% versus the 5%. They just show it much differently. Okay, this is an even tighter squeeze, allowing more in the tails. Okay, now why is that 0.9 right there? Okay, go back over here because that's 10%, right? Go back over here. We can use, there's some other things we could use, text formatting and so on, that we're not going to do here. Okay, just wanted to point out that you could put in text formatting. And there might be another version of this model coming up. The sample size we're also going to use in a couple of minutes. Now, we can also here, we don't need to report this, but we can do a third way in which we know what the sample standard deviation is. And this third way operates in this lovely format. Okay, here's our distribution of prices. So we have Tukey. We just did the percentiles with lower and upper, right? 2.5 and 97.5. 2.5 in each tail. We can use the fact that the average mu here is just the average that we would find. In our Indonesian case, it's 320. And we can also use the fact that this distribution is symmetrical. So we can actually say there's a lower and an upper. And the lower could be easily computed, although it's a lot more fun to use the simulation we did, as the mean plus or minus, but in this case, it's going to go minus how many standard deviations. So standard deviations are called Z's. Z's. Okay, the Z for a 2.5 and then a 97.5. How many standard deviations of those? Well, just putting in the numbers without figuring out what that Z is. Remember, we had roughly 46 and change. Okay, that's what that is. But we also computed it here. We know that the number was approximately 1357. Okay, fine. Okay, but if we had a back of the envelope and we knew that the min and the max of the Indonesian price gives us this, which is 46.40. We could do all of this in the back of an envelope, okay? Pretty much. What is it, 160 divided by 3.45, something like that, okay? If that's 46.40, great. If it isn't, write it in. Well, then the next question is, what is the Z? A time-honored way of doing this is to ask the question, if we transform all of our mu's into deviations scaled by the standard deviation, oh, there we go, there's something complicated, then we could write the Z as all of those mu's that we collected minus the average divided by standard deviation. And this will always be distributed as normal curve with a zero mean and a standard deviation of 1. Wow, because we can do that, because the distribution of sampled means is always going to be normal, we have a back of the envelope again way of calculating what that lower bound is and what that upper bound is. Well, that's the lower bound. The upper bound is going to look very similar. Okay, I mean, if you don't use X, you can use mu. I mean, we're all among friends here. So, and this one will be 320 plus whatever that Z is. There we go. Okay. So whatever that Z is, now what is that Z? I'll tell you right now, at a 95% or 5% tolerance, 95% level of credibility, 95% of the time, there's a probability of 95% that we're going to see a price between two things. Okay, that's the idea there. Two prices, two averages, actually. This will be the lower, and this will be the upper. Okay. So what is that Z? So because that Z is normally distributed, all we have to do is calculate this number. I already know it's minus 1.96, but let me show that. NORM.INV. See if I can remember how to do this. Oh no, it isn't norm.dist, it's norm.inverse. We're inverting, we're solving. So normally we solve for the probability, right? We've been doing that, lots and lots of probabilities. The inverse problem is to say, what is the probability, and solve for the mean. And it's to say the lower bound of this transformed mean. Here's the transformed part right here. So, okay, let's, doing a little bit there. Let me move this out of the way. So basically we wanted to put in here, no, what's the choice? The tolerance choice. Yeah, what is that number? It's going to, by the way, assume 0, 1. Let's type it in there. No true or false. Okay, we don't need that. That's norm disk. And it's minus 1.28. Well, why is it 1.28? Well, it's 1.28 because we chose a 10%. What if I went back to the traditional 5%, which was an example? Ooh, minus 1.64, almost 1.65, okay? If I went to the 1%, ooh, minus 2.32, okay? So this, you can see what you can do. You can increase the number of standard deviations. That's 2.32 standard deviations now. Okay, so we would take this number, the absolute value of it, to get the sign correctly. Okay, so it's 2 point, in either direction. Well, we would take the mean, and that would be the average of the indirect of something way the heck back up here. There we go. That thing, mean indo. Okay. So where is that? That's D3. Yep, D3. The thing we want. So we're building our formula. Make sure you have an equals in front of it. D. Yeah, let's keep putting a, there we go, because you might want to do this again. So it's 320. That was that average. And we're going to say minus the absolute value of norm.inverse of tolerance choice. We got to remember though, and I didn't remember, divided by 2. Remember, it's divided by 2. 5% would make it 2.5%. That's the number of standard deviations. That minus sign means it's in the going to the left, it's the lower bound. And this will be times okay, what is the population? Population. Well, the population is the max indo, which I think is indo underscore max minus indo underscore min. All of that divided by square root of 12. That whole quantity divided by square root of the sample size. It's way over here somewhere. There we go. Sample size also happens to be 12. Yeah, let's see what we come up with. So we have the average indirect, D3, minus the absolute value. Oh, we needed another one right here. Lots of, there we go. You entered too many somewhere. Well, that happens. So this one looks good. Average of something, and that indirect is of something, and that's good. Now we have the absolute value of something, and that looks good. And then we have those two, and that one, and that one. Too many arguments in the function. We need to have one more thing. Remember? 0, 1. Okay. 285 is the answer. Okay, now this is an equivalent lower bound. So let's just put it down here. And that's for the 99. Lower 99. Just half of 1%. Almost exactly on. Use exactly the same thing, but put a plus sign here. We don't have to work at this any harder than we should. And that's 354.92. So there, notice the simulation and the formula. And the formula is derived from max and min divided by root 12. You get the population standard deviation divided by the square root of what? Sample size. Okay. That's now the sampled means, and we had like 10,000 of those that we sampled. We took the means. That's the standard deviation of the sampled mean. That ratio of population standard deviation to the square root of the sample size. Sample size also happens to be 12. You can make it confusing for yourself if you want, but not confusing. Okay. Very, very similar. All right, fine. So we have 3 sheets to the wind now. 2 more will be coming up. One is, what if we are not sure about the population standard deviation? That this introduces a little bit more uncertainty into the problem. There's a trick for that one too. It takes into account the idea that that things aren't as Gaussian as they appeared. They might be a little bit with a little bit more oomph in each tail, which would spread out the z. It's called the t-score then. Okay, so that's another thing. We'll look at that another time. And then there's Chebyshev, good old Chebyshev. And we will also do that in a separate time, pretty much the same time that we will look at what it's called the Student-t distribution. But right now, let's be very happy with what we have done. We have done 2 more. Okay, we have Tukey's fences. We have lower and upper simulated. And we just saw that the lower and the upper are practically right on to the hand calculated version of the so-called truth here. Okay, so you gotta feel good about that. The only other thing we can do is put vertical lines in here. Okay, and that's a nice little exercise. Try it. And if you go into the course materials, the lecture in W.G. Foot's GitHub for Stats 1, you might get a little surprise there and get those verticals inside of this. But try it yourself. Not so hard to do. It's very similar to this vertical line right here. Very, very, very simple. Okay. And It will also reset whatever your numbers are, but you can play around with this all day, all night. Oh, that looks like fun. There's another thing. The user's going to love this. Yeah, there we go. Oh, another one. There we go. See, that didn't change anything. It did change the numbers down here, in which case you would have seen those two goalposts move into the center, allowing more room, more possibility of more range of high prices and low prices. That's exactly what's happening, and that's how you should be talking about it. I think we should be. All right, going to leave you with that. And I think we're going to say goodbye for the week, and hope you enjoyed this part 3 of lecture 10. Thank you very much for your kind attention, and I can't wait to get to lecture 11. It'll be great fun. Take care now. Thanks.